And I will pass the mic over to Sally McFarlane, who will introduce the meeting and our speakers.
Great. Thank you very much, Hazel. Thank you, everyone, for joining us today for this webinar on integrating Arctic field campaign observations and modeling. We appreciate your patience with the rescheduling of this webinar. As Hazel mentioned, a lot of things had to be rescheduled, of course, due to the shutdown. So this webinar is sponsored by the IARPC Monitoring, Observing, Modeling, and Prediction, or MOMP collaboration team. My name is Sally McFarlane. I'm at the Department of Energy, and I am one of the MOMP co-chairs. I'd like to acknowledge my fellow co-chairs, David Clemens Sewell and David Allen, who are online, and Kiki Schultz, who I think hasn't joined us today. And then also our coordinator, Hazel Shapiro, who is very ably coordinating this meeting. And if you have any issues with Zoom or anything, reach out to Hazel. So one of the objectives of the MOMP collaboration team, or whatever we are now, foundational activity collaboration team, is to coordinate activities and communities of practice that bring together Arctic modeling, observing, monitoring, and prediction to advance Arctic research. And so under this objective, one of our deliverables is to support the development of synthesis products, best estimate data sets, and model intercomparison studies using cases from major Arctic field campaigns and long-term observational sites. And so to facilitate this coordination of using Arctic field campaign data for model evaluation, we have organized this webinar, which will feature presentations about 2 recent Arctic field campaigns. The first one we'll hear about is the DOE-sponsored Cold-Air Outbreaks in the Marine Boundary Layer Experiment, or COMBLE. And then the second campaign is the NASA-sponsored Arctic Radiation-Cloud-Aerosol-Surface Interaction Experiment, or ARCSIX. So I'll introduce each speaker before they begin. Each presentation will be 15 minutes, and we'll have maybe 1 or 2 clarifying questions after each talk, and then we'll have more time for a more general discussion at the end. So our first speaker today is Dr. Florian Tornow, who will provide an overview and current results from the COMBLE Model Intercomparison Project. Florian is an associate research scientist at Columbia University and NASA's Goddard Institute for Space Studies. His research focuses on marine cold air outbreaks, combining field campaign data, satellite retrievals, and large eddy simulations and single column model simulations to better understand cloud evolution and cloud radiative effects. And he co-leads the COMBLE MIP, which is an international model observation intercomparison effort focused on evaluating cloud representation and models. And he also contributes to NASA GIS's modeling case library, which is an observationally constrained framework for testing and developing Earth system models under a range of synoptic conditions. So Florian, take it away.
Yeah, first of all, thank you so much for the invitation. While I share my screen and put it here in full mode. I would like to acknowledge my co-leads, Anne Friedland and Timothy Giuliano, as well as the great support from DOE that made this, facilitated this infrastructure. You should see it as a full screen mode now. And the MEDI modeling groups that participated. Okay. So much of what we do has to do with better understanding cloud and precipitation processes. And these are highly relevant because these processes determine the feedback mechanisms that these clouds and their radiative effects will undergo. One of these feedback mechanisms is cloud phase feedback. As you can see in the bottom sketch there, some clouds that may currently be in sub-zero temperature and consist of both liquid and frozen condensate may, in a future climate, solely consist of liquid condensate, which will render them less efficient in their precipitation. They reduce the precipitation efficiency and makes these clouds efficiently brighter by increasing their optical depth and their amount. Now, these feedback mechanisms drive the global uncertainty of climate projections, or often termed climate sensitivity, and also impact uncertainty when it comes to projections of Arctic amplification. Now, we use marine cold-air outbreaks that are frequent and widespread in the mid and high latitudes and are associated with strong radiative biases in Earth system models, most prominently over the Southern Ocean. And these cold-air outbreaks are also great natural laboratories that lend themselves to atmospheric study and are expected to be subject to these uncertain feedback mechanisms. On the right side, I'm showing you the case that the Model Observation Intercomparison Project centers around. This is from the COMBLE campaign, a strong cold air outbreak. Now you can easily see what happens here. The cold air comes off the ice, and to sketch this, we get this relatively cold air coming either from the pack ice or from a cold continent that will then meet relatively warm ocean waters that spurs enormous surface heat fluxes that then sort of create this slowly deepening boundary layer in which clouds can form, and at some point, as they deepen and progress, precipitate and undergo cloud regime transitions, first from a more overcast situation where clouds may be organized as streets, towards a later stage where they part and become more convective in nature. And in this example, for example, the scene albedo is cut in half. So these clouds undergo strong cloud regime transitions. Now, natural laboratories suggest that we should root our efforts into field studies where we have comprehensive observations. And one of those is COMBLE. At the end of 2019 through roughly the middle of 2020, DOE stationed an ARCSIX here in the north of the Norwegian continent. And here we can see that in this example, the end stage of such a cold air outbreak is measured. Now, the tricky part is to connect this with modeling. In our case, we model air mass history. So we want to understand how an air mass evolves from a cloud-free stage towards a cloud formation process, and then later towards an end stage. So we're looking for initial conditions further upwind. And they're here provided by the Mount Zeppelin station on Svalbard. So during this COMBLE campaign, during these 6 months or so, we checked which Lagrangian trajectories would connect this downwind arm site with an upwind site here on Svalbard. And we identified roughly 5 cases in which this is the strongest one that we selected then for the intercomparison. And the Lagrangian approach here then opens the door for quasi-Lagrangian modeling, where we have a relatively small domain that can be 20 kilometer squared or 100 squared that moves and translates along this Lagrangian trajectory, sort of starting over the ice in the north and then arriving at the Norwegian continent. This minimizes computational cost because it's fairly efficient to run these simulations. It minimizes advection effects as this air mass moves with the boundary layer wind. And we can focus solely on the evolving cloudy boundary layer that we simulate. We run 2 types of Lagrangian models here. One is quasi-Lagrangian large eddy simulations that largely resolve the scales relevant for the dynamics. Often parameterizes still the microphysics, and is here used to identify the plausible forcing and configuration, first of all, and then second, to serve as benchmark to the second type of simulation that we run, which is single column model simulations, which are here a proxy for the column physics in a parent system model. It's literally a single column that knows the physics of the parent model. And typically, dynamics and microphysics are parameterized. And given the identical forcing, we can then check how well it compares against large eddy simulations. On the right side, I'm showing an example here using the Dharma LES in blue against the NASA GISS Model E SCM in orange. You can see the x-axis is time. So 0 roughly means we're at the ice edge. Negative values means we're over the ice pack. And then everything positive moves over to the Norwegian Sea up until 18 hours when we meet the arm station. There's several panels shown here. At the top, we have sensible and latent surface heat fluxes, and we have cloud properties. It's cloud top height, cloud to temperature, optical depth, liquid water pass, and ice water pass. And I'll talk a little bit in a moment about the differences between LES and SCM. For now, I want to make sure that these LES simulations indeed are plausible. And so we take a range of observational targets here to ensure that. Ideally, these observational targets have very few or no retrieval assumptions. They ideally are independent of viewing elimination geometry issues and are frequently available. And these type of data are hard to find. Before I show data, we use upwind observations, as I said, that serve to give us ground-based aerosol information and also profiles of temperature and humidity that guide our model setup here. And then, of course, there's ARM data. That's the comprehensive data collected at the end. So we have active instruments, LiDAR and radar, passive ones, that's a microwave radiometer and a multispectral, hyperspectral radiometer at the ground, and then several in situ probes, an aerosol observing system, flux measurements, and radiosondes. And they provide a whole range of properties that are now available to us to constrain these simulations. So I'm already showing dots here that come from reanalysis for surface fluxes, ERA5 and CARA. We don't use this as observational constraints, but like to at least peek at these to know if we are in the ballpark of greater models. So here I'm now showing E-core and bulk fluxes that roughly tell us that we indeed simulate okay surface fluxes. There's cloud top height at the end shown here, reaching 4 kilometers or so. So these clouds deepen indeed from 500 all the way to 4 kilometers. And then there's cloud top temperature when combining radar and radiosondes. There's a RAD flux project that gives us cloud optical depth. There's liquid water pass coming from 2 different sources here that tell us that we're also in the ballpark. Now, so far, I've shown you only data at the 18 hours mark, and there's no ice water pass retrieval, as these are notoriously tricky. Thankfully, there's overpassing satellites that we can also fold in here. So there's opportune moment where Calypso overpassed at the early stage of this trajectory. So we have here now cloud top height, temperature, optical depth, and ice water pass, thanks to the thin clouds early on. And these all suggest that these simulations look okay. Then there's MAC liquid water pass that I'd like to highlight here. This comes from multiple satellite platforms that all carry low frequency microwave radiometers that are largely blind to ice. And so now you can see in panel F that this makes for a great temporal coverage where we get liquid water pass that's here lumped cloud and rainwater. And that suggests that liquid water pass is relatively stable throughout this case, which is characteristic for strong cold-air outbreaks that are not so much dominated by liquid, but rather by frozen hydrometeors. And there's Cirrus that also stems from a fleet of satellites, and here that gives us top of atmosphere fluxes that are not showing on the right. And very lastly, Modus and Veers that are here, unfortunately not available because the retrieval conditions didn't lend themselves to using that. But we can still use imagery information to quantify cell size. That's not shown here, but I can at least show you the qualitative comparison that we do. So Veers had several overpasses, and there's an early one around 4 hours where we now can compare Veers imagery against the 2D pseudo-albedo from the models. And while we don't get the same cell size or the cloud street organization, we do indeed get the increase in cell size towards the later stage at about 16 hours, where these cells increase. And there's notable differences that future research might tackle, such as our updraft regions too optically thick, and are the surrounding sort of outflow umbrella regions too optically thin. But that's subject to future research. So as I said, there's already a few differences between LES and SCM visible. And how do we now assess strengths and weaknesses of a single color model? We here choose a stepwise increase in model complexity, where we start with a relatively simple configuration. That is, we only permit liquid in these simulations and we fix microphysics, and move then towards more complex one, where we allow frozen hydrometeors and treat aerosol and hydrometeors fully prognostic. In COMBLE MIP, this translates into a 2-part sort of configuration where we have part 1 and part 1A that we only have liquid, and here we fix cloud droplet number concentrations ND. And then in part B, we permit both liquid and frozen hydrometeors, and here fix both ND and NI, which is the frozen hydrometeor concentration. So the panels I've just shown you are now shown again in 2 columns and for all LES participating groups, which are roughly 10 at this stage. So we have liquid only on the left side and mixed phase on the right. And at first glance, there's not too much different between the 2 columns. For example, surface fluxes remain relatively similar. But for example, liquid only runs tend to deepen a little more, which makes for colder cloud tops. It makes also for optically thicker clouds, as all liquid now is in the liquid phase and none is in the ice phase, as shown at the very bottom. And so obviously these simulations now separate themselves from the observational targets, so they're somewhat idealistic, but they're still very useful to understand when models start to diverge from one another. So these are all the LES runs, and now I'm showing all the SEMs runs from the 7 groups that participated. So as you can see, they do indeed form clouds at a similar moment and then deepen them realistically. But there's a few properties that do not align with LES, and I'm going to talk on that for the remainder of this presentation. So for example, when focusing on liquid clouds and looking at the outgoing top of atmosphere long wave radiation, LES and SEM shown as dashed lines and LES as solid lines, largely agree that normalized here towards the first value of, so that's showing 1, that these outgoing long wave fluxes tend to slowly decrease over time as this cloud deck is fully overcast. And all that happens here is the clouds become slowly colder as they deepen, and so there's less long wave radiation emitted. And then near the surface and the downwelling long wave radiation, we can see a stable or slight increase of long wave fluxes as the base of these clouds remains at a similar height, but the clouds slowly warm over time. Now moving to mixed phase conditions, you can see a much wider spread in conditions, though LES has more than, doesn't converge as well as for liquid only. And you can see that SEM separates itself from the bunch here. The LES says there's a stable or slightly increasing outgoing long wave flux at top of atmosphere. And that has to do with now the fact that the cloud cover is below 1, so the cloud deck is not fully overcast anymore. So the top of atmosphere sees both cooling clouds and increasing amounts of surface. So that makes for a slight increase perhaps in the outgoing long wave. And
2 minutes, Florian.
oh, thank you. However, single column models tend to do the same thing as for the liquid only scenario, where we still decrease in outgoing long wave. It has to do with the fact again that these models remain overcast. So these SEMs seem clearly challenged to capture this cloud radiative effect. We can now just condense this information to a plot like this, where we build the ratio of liquid only over mixed phase simulations. So in other words, going from a mixed phase scenario to a liquid only one will increase cloud cover in parts by a factor of 6, which will also increase the downwelling long wave radiation at surface and decrease the upwelling at top of atmosphere. And you can see that the dots, the LES, span a certain range. However, the SEMs all hover around 1, which suggests that they're very insensitive to this change. And similar for optical depth, there's a huge change going from mixed phase to liquid only. And the only model that's reported consistently optical depth, which is model E, does an okay job, seemingly. So I hope to have convinced you that marine cold-air outbreaks are a great natural laboratory that help us understand cloud and precipitation processes. The observation-constrained quasi-Lagrangian framework enables side-by-side simulations of LES versus SEM. And in this simple setup that I've shown today, where we fixed hydrometeor concentrations, we can see that SEMs are challenged here and retain the cloud deck when switching to mixed phase conditions. There's more work to be done. Conduct part 2 and understand what happens when we add model complexity and what deficiencies come with that, and focus particularly on cloud morphology, as I alluded to. So, for example, find out to what degree are cloud dynamics and thermodynamics represented okay, and how are they changing, and do SEMs represent that and these cloud transitions. Thank you for your attention.
Great, thank you, Florian. Do we have any quick questions for Florian? Okay, so if we will have time again for discussion of both talks after the second one, and in the meantime, if you do think of questions, you can put them in the chat. Our next speaker will be Dr. Sebastian Schmidt, who will talk about a more recent field campaign. Sebastian will highlight the data collected during the ARCSIX aircraft campaign. Sebastian earned his PhD in meteorology from the University of Leipzig after studying physics in both Germany and Scotland. He is an associate professor in the Department of Atmospheric and Ocean Sciences and at LASP at the University of Colorado in Boulder, where he specializes in aircraft, ground-based, and satellite observations to understand aerosol cloud radiation interactions. His group has fielded radiation and imagery instruments for numerous aircraft campaigns around the globe, and he served as the science lead for the ARCSIX campaign. He also leads the development of a limb-to-limb multi-angle camera that is going to fly on the NASA Libera Earth Radiation Budget mission. So Sebastian, please.
Yeah, thank you for having me. I'm happy to talk about ARCSIX, and I will probably breeze through these slides because I would really like to come to the cloud lifecycle questions that have come up fairly recently. I would say over the past few weeks. We have a few papers even coming, and there's data coming out. Before doing that, though, before breezing, I would like to also give credit to NASA, of course, for sponsoring this pretty large campaign in Greenland, but also to the ARCSIX team. Patrick is actually present. He's one of my co-conspirators, but highlighted here is the ARCSIX science team and my group in particular, who've been looking at a lot of the data already. So this shows a few scenes here from the campaign. So students did a lot of the flight planning and everything, actually, the flying of the instruments. The team was relatively small. You see 2 out of 3 aircraft standing here in the hangar. Logistics was challenging, but we did it. So in terms of the science, what were actually some of the challenges that we were looking at? So I'm showing this in pictures rather than in formal science questions. One of them is illustrated on the left in a video. So what you see here in this video frame is a scene over ice where you have patchy clouds. Those would actually not be detected often in satellite imagery, and that is a big problem. Up to a third of clouds are not detected and by satellite imagery, and that means one might underestimate the warming effect of clouds on the sea ice. And so, of course, that affects the melt later on. This is actually where ARCSIX originally came from. And then we added a lot of other objectives to it, including cloud life cycle. Originally, it came from a remote sensing and surface radiative energy budget perspective. On the right-hand side, what you also see is, speaking of texture here, is that once you get ponding, for example, in the summertime, so we stretch the campaign from the spring all the way to the summer, spanning as much of a melt season as possible. So you get this structure here, which also can't be resolved by imagery. And the question is, how do you then actually understand how the melt season proceeds when you have this, what I call differential melting here. So to just show you here the contrast between the spring as we encountered it and the summer, again with the same picture. So in the spring you have these sastrugi and ridges and leads, and some of the angular structure of the surface reflectance is actually not well resolved or captured in satellite observations. That was another objective. It turns out that actually there is no operational NASA product for either albedo or the reflectance available, which is, of course, a problem because the albedo is the primary parameter needed to understand the melting. So right now we're often relying on climatologies in this regard, which is problematic because there's so much change, especially as we're going away from multi-year to sea ice to seasonal sea ice, as you can see here on the right-hand side. I'm gonna start with an apology here because the data location that I have here on the right-hand side is the preliminary field data location. Honestly, it is better to understand and digest at the moment than the permanent archive. We're in the process of moving over to a permanent archive at Langley. That will be published very soon. It's already available, but I recommend that if you're interested in the data, that you go to the temporary site for now. So that's where you can find it. So I'm summarizing here in the middle what the overarching objective actually was. I already told you that we tried to span the early spring to the midsummer conditions of the sea ice. We were in the Pituffik space station here. Down below, you can see our collected flight tracks with our 3 aircraft. And of course, the overarching objective was to understand the sea ice melt in response to the cloud aerosol and surface properties, as well as precipitation, while also improving remote sensing. So some of the sensors that we fielded were never flown before in this constellation. All right, here now you see some of these results. We're not so interested here in this particular meeting in the radiation piece, but I just wanted to nevertheless contrast how different the surface conditions actually are. And that's reflected, no pun intended, in the lowering of the surface albedo as we go on in the season. There's going to be a paper coming out on that soon. Here, that just illustrates once more this problem of these undetected clouds. So there was actually a previous mission in 2014 that confirmed that problem that Gen K had previously observed or discovered with Calypso observations. And that is mostly a problem in the long wave, again, because you're missing some of the warming, especially when the sea ice is still there. So, overview of the campaign. This was what we had planned originally. So most of the operations were going to take place in this coastal corridor, but we ended up flying actually north of Ellesmere Island over here as well. And some of the typical patterns were either the clear sky flights that I just showed you an example of, or we would fly these, what we call these cloud walls, where we would fly below the cloud, measuring radiation, precipitation, aerosols, and turbulent fluxes, all of these things. Fly above the cloud, doing the same thing, trying to capture INPs, etc., and then porpoising through the cloud to get the thermodynamics and the microphysics with imaging probes, wing probes, and bulk probes, and these kinds of things. So what you see here is from left to right, the collected payload on the 3 aircraft. On the left here, you see the NASA G3 serving as a remote sensing platform. In addition to a spectral imager, AVERS, as well as the water vapor Langley LiDAR halo, it also carried a dropson system, which was really useful to get the whole thermodynamics from high up all the way to the surface. Our workhorse was the NASA P3, and that carried a lot of remote sensing as well that I'm not going to get into, but also radiation, in situ observations of clouds, turbulent fluxes, water vapor, aerosol properties, INP, CCN, hygroscopicity measurements, etc. It also carried a LiDAR that served as a snow topography LiDAR because we wanted to understand the topography of the underlying sea ice as well, the thickness of the ice and snow, etc. And lastly, we had the Spec Inc. Learjet flying through the clouds as well, sampling cloud microphysics, and it also carried a precipitation radar. I'm going to skip through this really quickly. We have these videos available that visualize the progression of the campaign for the spring and the summer. So what I will highlight is that when you have these lines here, those are our so-called cloud walls. And when you have these DNA-looking shapes here, those are our surface maneuvers that we did. As for these cloud walls, so Florian just mentioned the Lagrangian strategy. We try to actually pursue a Lagrangian approach where we would sometimes put multiple of these walls spaced by basically the moving wind to make sure that we capture air mass as it moves along the streamlines. That sometimes didn't work and sometimes it did. So this is just an overview of the statistics here that we have, how many flights, how many hours, etc. I already told you types of flights. Ice survey and tracking, not so interesting for this community here. The most interesting piece are these cloud stacked legs with up to 3 aircraft. And then, of course, the associated aerosols. Sometimes we would also capture a transport event of aerosols. For example, we had a volcano in Iceland that we think we captured with some of the flights. But there were other things as well of interest in terms of the motion of these aerosols. I would just like to breeze through some of these examples here. This is the topography LiDAR showing these ridges and leads and so on. This is the water vapor LiDAR, just as an example. And the intercomparison with the dropsons. So this is probably the data that is of a lot of use to many of you. This here is the beautiful imagery from the spectral imager that was on the G3. This here shows some of our measurements in the lower left here of the albedo, but we didn't just do that. We also tried to tie it to the satellites. We had a camera on board, and we're actually in the process of developing that operational product that is so badly needed. We now do have the validation data, the airborne validation data to do so. So that's going to be really important. Something about clouds here. So we didn't get much into the cloud detection bias, but what we did find, so this is from a paper that's going to come out, bear with me here a little bit. One of the things we found was that the clouds that satellites retrieve in the area are notoriously too high. They're always, no matter which product you use, Modis or Virus, it's even worse in Virus products than in Modis, they're always too high. I'm not going to get into the details here why. We know why. Just had a discussion about this yesterday again. So the satellite retrieved cloud base heights actually are shown in blue here for the summer on the right and for the spring on the left. And the actual cloud locations, as determined with our in situ observations, are shown in green. So that may not, that looks terrible, but this also should give us pause in terms of thinking about cloud lifecycle. Are these clouds actually coupled to the surface or not? Most of the time, they're not coupled to the surface, but still, your satellite retrievals tell you a completely different story. The other thing that we found out was that early in the spring, turns out that if you believe the satellite products, the clouds would actually cool. So those are all of these data points here. Won't get into detail here either. Under that dashed line. So below the dashed line, you have cooling. Above the dashed line, you have warming. And it turns out those clouds actually warm. Most of the clouds warm in the spring, the ones that we looked at, these typical boundary layer clouds. And that is because the albedo that is fed into the RT model is wrong. So the current products get it wrong. So we went out there and measured and got the truth. And so we know that those clouds warm primarily. So with the remaining time, I'm gonna get you to the real interesting stuff, which is the microphysics observations in combination with some of the LiDAR observations as well. You can always later go to these slides and digest this. This is excellent work done by Ewan Crosby, using some of our Lagrangian observations to see how the thermodynamic structure actually evolves. And in some cases, you have, say, one layer that's dying, and you have some feeding of this layer underneath. This year is one of
2
these
minutes,
cases.
Sebastian.
Pardon?
2
Two?
minutes.
Yeah, okay, that's great. So then we had 3 days in a row here where we measured an air mass. You can kind of see how the dropsond locations actually progress over time here in the location, and you can then connect those dots in terms of modeling. I And that's actually starting to happen right now. Amy Solomon is using a nested approach there, where the inner nest is basically the LES domain, and moves with um, that moves with the aircraft data, or is able to move with the aircraft data, essentially. One thing I wanted to point out before we finish here is that a lot of what we observe, just like in the outbreaks that you talked about, but we don't have cold air outbreaks here. These are vanilla Arctic clouds in the in the summer. We often observe this cellular structure here, and often in our case, the ice that we have so many questions about is in the updrafts. But I talked to Matt Shoup last week, and he said the ice isn't necessarily always in the updraft. Sometimes it's actually the opposite. It happens to be in the downdrafts. The question that we had was, why do we actually have so much ice? And why do we have irregular shapes, such as the ones that are shown here? So something special about ARCSIX was that the cloud tops were around -2 to -7 C or so, and yet that's where we had a lot of ice. The problem is that the secondary ice process, so primary ice production, we had a problem with that because we measured way too few INP. To explain this, secondary ice production, Alexei Korolev ruled out most of them, or all of them, as a matter of fact. And in addition, seeding from above was also not possible because it was actually often warmer. So we had above freezing temperatures above these clouds. So we have a little bit of a problem there. Um, and we have this problem of lack of closure between the INP and the ice that we measure in the cloud, but not necessarily the aerosol precursors. So I already said the thing about the updrafts, downdrafts. I wanted to ask the question whether any of you have read this paper by Knopf et al. 24, because it basically introduces a scheme where you wouldn't have this problem of the lack of INP. That's all I'm going to say here because I'm out of time. Instead of a final slide, I wanted to show you the overview of our data workshop, and there is the link here. Shortly here, we will actually have this clickable where you can click on data sets of interest, and you can get to the presentation that talks about them, and also the location of the data and where things were, etc. And I will finish with that and take any questions.
Great. Thank you, Sebastian. Any questions for Sebastian? There is a question that we got from, let's see, so Twyla Moon was not able to attend, but she had a question which I think is relevant to this general discussion and to both speakers, which is asking whether what methods or processes did the field campaigns use to ensure that the data would be most usable by the modeling community? So maybe the question might be actually were any methods or processes used to think about that? And then kind of in retrospect, any lessons learned or recommendations in what future field campaigns might think about. So any thoughts on that, Sebastian? And then I'll go to
Yeah,
Florian.
I can start with this. So we actually did have model understanding in mind when we designed this. So one of the most important things that we did was a stringent co-location of not only aircraft on top of each other, but also we had a number of buoys that we overflew regularly, and we underflew satellites regularly, as well as ground stations and icebreakers. So the co-location, as well as the tracking of the air masses, was something really fundamental. What we haven't done though yet is we haven't publicized, let's say we didn't publicize the trajectories yet. There are so many things that can be done. Anyway, this would be something that should be done maybe to see how these actually connect. Yep, that would be my answer.
Thank you. Pat, did you want to add more on that?
If possible, just to add to what Sebastian said, a couple of things that we did in order to make sure, or ensure as much as we can that the observations that we took are relevant to modeling is in the construction of the white paper. We definitely consulted a lot of modelers and had, I know, well, Anne Fridlin in particular was involved, but we had several folks and we tried to bring in, and Sebastian was really key in this, bringing in as many modelers as we could and talk to as many people as we can so that in the formulation of the experiment, modelers' input was there in formulating the science questions and in formulating kind of the observations that we needed. And then during the lead up to the campaign, we did a number of dry runs, and we developed these flight plans, like that flight plan that Sebastian talked about, the cloud wall one. That was developed in particular to focus on cloud life cycle science questions in the lead up to the campaign in coordination with modelers. And so we brought them in. Again, Sebastian was really key. Like, we need to bring in the modelers here. And so we brought in the modelers, and we were thinking about the pre-campaign designs for flight plans. I would say, a shortcoming that I would love to fix in the future that would just say, when you fund a campaign, even as like, let's say, well funded as I think ARCSIX was, even though it's logistically expensive. So it was kind of a lot of money, but we would have loved to have more people in the field to help, for sure. As Sebastian says, we had a skeleton crew, which we did, but it would be great to have more modelers in the field. But it was just like the budget, we didn't have the budget for that, essentially, is how the conversations that happened from a program management perspective that we had are, well, do you want more observations or do you want more modeling? And so it goes back to this philosophy where if you don't take an observation, you can't go back and do it. And so there's always this focus on taking more observations. And so I think in lieu of having more modelers in the field to help us, make tweaks to the plan and to pick where to fly, maybe better. I don't know, better. I thought we did a pretty good job. But, in lieu of that, I think making sure that you have modelers helping to design the campaign and develop the flight plans you're going to use in the field was one of the key things I think we tried to do to make it as useful as possible to modelers. Sorry for a long-winded response.
I would maybe add one more thing to that, because I think that's important. We did have Amy Solomon in the field in the spring. We did have Alexei Korolev there, who's not a modeler, but who knows intimately about secondary ice production, for example, and some other experts. For example, Ralph was there at some point, Lauren Zamora was there. And the nice thing about that is that Alexei, for example, would step off the plane after flight and he would say, I can't believe what I just saw, all of this ice at -2°C, and then no ice, all liquid, at way colder temperatures. What is happening here? And that actually was real-time information that we could turn around into then flying into these conditions again and prioritizing those that would inform us the most and maybe answer these questions.
Yeah, it's exciting if there's something about ice that Alexei hasn't seen. Florian, do you have any thoughts as a modeler on what observationalists could do better?
Yeah, I think I kind of try to come up with ideals that observations should have, and we try to stick to that as much as possible. Sebastian always also told about this cloud height bias in retrievals from VIIRS and MODIS. And we, to some degree, also saw that. And I think it had to do with the pixel size that we could sometimes see cloud, but also warmer ocean underneath, and that made for a seemingly warmer cloud top, and that put the clouds at the wrong level. At least that's what we sometimes saw. So we try to rule out everything that could be biased with any of these retrieval assumptions that we became aware of. One thing that we have not done yet across all models, but we're planning to do, is perform instrument simulator post-processing on simulations, which I think will open the door to especially use LiDAR and radar data more intensively that may be hard to derive products from, but it allows for an apples-to-apples comparison where we bring the model actually to the observation level 1 type of category. And then, yeah, I love that ice question, Sebastian. Like, where is it all coming from? I think, yeah, Daniel Knopf's paper is maybe, yeah, one of the answers. I don't know. But it's, yeah, it's always good to make the model community aware of this, have this dialogue, right, even in the field. And I think some of the models that participate in part 2 of our campaign, they will adopt the ENAS approach from Daniel Knopf, where we tie INP to the prevalent aerosol in the sense that, yeah, there may be more than just temperature suggests there should be.
I'm so glad you said that, because when I heard about this and then discussed it with others, they said, well, that's an idea that's out there somewhere. And I thought, well, maybe it isn't just the temperature. And Matt Shoup even, thought this, something similar when I just talked to him. Anyway, Ralph has his hand up.
Okay. Yeah, I was just going to add that I think there's really no substitute for having the modelers in the field directly involved. I mean, in our team, we had Pete Calarco and Lauren Zamora and myself. And when we had this volcano event, for example, it was the interaction between the 3 of us and several others that made it possible for us to really get a good data set, for one thing, and also to brainstorm ideas that improve the whole effort, which is still ongoing. So yeah, just very important to have the modelers directly involved at the time, not just after the fact.
Great, thank you. Any other questions or thoughts? So I think, one of the things that is interesting and that came up in both presentations is this, these Lagrangian studies and trying to follow the air masses and understand the air masses. And, as somebody who manages a ground-based observational site, that's obviously a lot easier to do with aircraft than it is with the ground-based site. But it's interesting to see, the models also following these Lagrangian tracks. So is this, I guess, just something that we think is pretty important to think about in future observational campaigns, and ways that even with the ground-based measurements, we need to be thinking about adding other capabilities to try and get more at the, the upwind, at least an upwind site like we had in COMBLE. Any thoughts there?
I think it depends a little bit on the science question, but for ARCSIX and also for COMBLE, the way I understand it, it is key to have that. And you don't have to measure all of the parameters everywhere, upwind and downwind, but if you measure at least the key ones, that is already useful. For example, the G3 would sometimes, they would fly early on and they would just plant drop zones everywhere. And then later on, nobody else was there at the time, but then the next day you would then focus. See what I mean? So you can strategically mix and match. You don't have to do everything.
Yeah, and I think Sebastian described the heavy lifting in the field, right? Like where you have to live look at the trajectories and make a decision what seems to be a good target the next day. But I think it's worth doing this heavy lifting in the field rather than way after the fact when it's unclear what's exactly usable and what's not. But I think, yeah, doing it in the field might be the better approach.
Yeah, to add, I think, so to address your question, I think using more of these Lagrangian approaches in the future could be really powerful, especially for these cloud lifecycle questions where it's really beneficial when you can quote unquote control for the advective terms, right? And just kind of focus on the physics that's happening. And so that's kind of the real power in that, in what Florian was showing. But question I have here is though, we took one approach, right? Using the Lagrangian, air parcel tracker kind of, and kind of jump different places to kind of chase the air mass every day. But, and Sebastian might be able to explain this approach better than I can, certainly in the moment for sure. I'd have to read it again. But in, what was the name of Manfred's campaign? The AC3 and
AC3, yeah.
The AC3, they took a different approach to Lagrangian to identifying the parcels, and I would say they argue they took more of a statistical approach in getting at it. And so I would say like there's still work to be done, I think, to figure out which of those approaches would be more successful, because we talked about this in the lead up and doing those calculations. There's lots of uncertainty when you use those Lagrangian parcel trackers. You're based on the forecast, right? You're trying to know what the forecast is and guess the next day where your parcel is going to be. And so there's certainly uncertainty in that. So while I think the approach is definitely useful in Lagrangian way, I don't know if we've come across the best way to implement it in the field yet.
It did work pretty well, I would say, it sometimes, even one-day Lagrangians when we place the walls at a certain distance. And I just don't envy Amy, who's using all of this data right now, but she made a really good start. Oh, she's here!
Yeah, she's here. Maybe that's where the rubber meets the road, right?
Yeah.
Where we're successful, it depends if a modeler can use it or not, right? That's how we know if we're successful. Go ahead, Amy.
Putting you on the spot, Amy. If you're talking, we can't hear you. I saw that you came off mute.
Can you hear me now?
Yes.
Yeah, I am using all of this information in my modeling study to try to track the air mass and the evolution of the cloud from 2 days before to our cloud wall north of Greenland. I'm finding it's challenging to compare trajectories to tracers. It's not, the air mass that we did track 2 days before our cloud wall does get to the cloud wall, but I'm finding that there are trajectories from other places, such as the North Pole, that actually contribute more of the air in the cloud wall than we had anticipated. So I am finding it's challenging, but I'm trying to use all of the information that we have from the campaign in the modeling study.
Great, thank you. Yeah, that's interesting then.
Okay, I know we're close to the end, but if there are questions, you can stop me. But I was going to make a crazy recommendation or a suggestion out there for how we might be able to do this faster or better, and it'd be really hard on the modelers. But look what Ralph is saying is that, and what Sebastian alluded to about having Alexei there to be like, oh, I've never seen that before, right? And so what we did, what Sebastian really pushed for in the field was that we iterated on our flight plans. We had, an 8-week total campaign, so we could actually learn as we were going and try to do it better. And so it'd be awesome if there was some in the field modeling capability where you can, like, in really rapid succession, run these case studies, like in preliminary mode, and right after you take them, within a couple days or a week or something, so that we can learn, like, speed up that feedback loop, right, where you can actually make adjustments during the case of a single campaign. I think we were able to do that with some of the science questions, but again, in this the cloud lifecycle, and have it, for it taking essentially a lot of time for you to get these case studies spun up, that's kind of impossible. But I wonder if there's like a simplified toy modeling approach we could use to maybe speed up that feedback loop where you can learn in the field and make adjustments during a single campaign instead of having to wait for the campaign 10 years later or 5 years later even, right? So
yeah, interesting thought. David?
Yeah, just to follow up there. So, I mean, Patrick, I love that idea. Obviously, I think that would be awesome. And I mean, you sort of talked a little bit about the logistical challenges of like actually setting up these case studies, having the forcing data, processed and ready to go quickly enough that could be run. The other thing I think would be maybe worth discussing is the sort of funding logistical challenges here, right? When you want to fund that modeling study, typically you already have some, right? The field campaign data is already there, and you can point to, hey, this doesn't line up with our model. In this case study, you know, there needs to be more funding devoted to understanding why this is from the modeling side. And so I don't know how one would go about sort of saying, well, we don't know yet what thing Alexei is going to see in the field that he doesn't, that he's never seen before. But we're pretty certain that if you do a comprehensive enough field campaign in an interesting area and time of year, there are going to be these things, and it would be, you know, actually a net positive to fund modelers to be in the field and do this in person, or this sort of rapid cycling in advance of knowing what they're actually going to be. You see how that could be a disconnect in the way that things are often funded.
I mean, I think that's a good point, but on the other hand, presumably you're going and doing these observations for a reason, right? There's some reason that we think this is an interesting place to observe, and often we try and motivate that by it's a gap that the models aren't doing well in. But it is a bit of a chicken and egg, right? Yeah. So it's, I mean, we have that concern sometimes too. We don't know necessarily, field campaigns don't always go as planned, and so sometimes you don't get the data you're expecting to get. So if a modeler was planning to do a particular, well, anyone was planning to do a particular thing with the data, and then you don't get that data, right? You have to make some changes to your plans, but you know, we're used to that, I guess, and in our field, having to make changes to plans. Okay, we are at the top of the hour, so I want to thank our speakers again. This was very nice presentations and very interesting discussion. And maybe we can follow up some of these themes later in some future meetings. I think right now MOMP doesn't actually have a next meeting planned yet. We're working on some ideas, but stay tuned to the IRPIC page. Hazel has posted where the recording will be posted, so you can share it with all your friends and colleagues who weren't able to make the meeting today. And then, as Hazel mentioned at the start, some people might not have been on then, IRPIC is having listening sessions about the next research plan. So we encourage all of you to join those and make your thoughts known. So thank you again to Florian and Sebastian, and to all of everyone who attended. Thank you.
Thank you all.
Thank you, guys.
Great presentations. Thanks, guys.